I would be delighted to have this opportunity to share some of the ideas and developments we have on how machine learning combined with the microscopy can enable materials discovery. And obviously, if these ideas spark the conversation and future ideas how to scale it to new material classes and new applications, that would be fantastic. So as advertised, I spent the first half of my career at the DOE User Center, the Center for Nanophase Materials, Nanoscale Materials. So throughout this time, I had joint affiliations with the University of Tennessee, Knoxville. Then for the second half of my career, I decided that it's time to move to academia full-time. The only unusual, I mean, it's quite common, in fact. The only unusual part about my career pathway is that I spent a year in industry in the Amazon Moonshot factory, basically to have an idea of how the scientific concepts are de-risked and how they are transformed into the products and businesses. So very useful skill set to have. So I started to work on the applications of machine learning and experimental sciences almost 20 years ago, purely driven from the experimental side. And in this presentation, I will basically illustrate how some of these ideas transform from simple data analysis into the actually automated experimentation. So all of you are familiar with this paper by Dane Morgan and Gerd Sider, published almost exactly 20 years ago, so the 2006, which basically combined the high throughput computing and machine learning. So the computers at that time were becoming powerful enough in order to calculate multiple material classes. So if you have multiple predictions, you need to somehow sort out through the results. And it turns out that machine learning is absolutely fantastic in organizing and finding internal relationship in the large volumes of data. And this paper 20 years ago was an inflection point, giving the rise to this high throughput computation revolution. So now you see the papers coming out from companies like Google, Meta, Microsoft, when they dedicate their online cloud power in order to calculate new material classes. However, we know that predicting materials is actually not enough, right? So you can sort of predict small molecules, to some extent single crystals, but real materials are much more complex than their idealized representations. So for example, in the single crystalline silicon, the properties are not controlled by the lattice itself. It's actually controlled by the dopants, and it's very difficult to run the predictive modeling for small dopant concentration. You just need to have a very large unit cell. Also equally important, for each new material, we care not only about the idealized predicted properties, but we care about the real properties, we care about manufacturability, and we also care about the cost. So to make a quote from the Oppenheimer movie, so theory and by the same token, machine learning can only get you so far. So at some point, we need to transition from predicting materials and predicting molecules to actually going in the lab and doing that. So when I joined University of Tennessee about 2 years ago, it already had a pretty established foundation in the high throughput synthesis. So some of my colleagues worked on the combinatorial synthesis for more than 15 years, including the classical combi growth, including the combinatorial laser processing. So University of Tennessee was one of the first places in the US to start the high throughput synthesis lab in 2019. So we started with a small Opentron robot that allowed to increase the throughput for the hybrid perovskite manufacturing by about a factor of 100. And this effort grew to multiple robots and the spin board that allows the in situ synthesis and characterization of the film. So you can basically drop cast the film, put it on the plate, anneal it, and detect the PL signal in the process. So once I joined the University of Tennessee, my focus has been on the development of the automated characterization capabilities. So my group works on the scanning probe microscopy. So we integrated the SPM with the UT supercomputer. So we can send the data to the supercomputer, analyze it, and return the control signals back to the system. So we worked with my colleagues in electron microscopy to build the same type of effort in the electron microscopy field. So we have the same type of capability for Spectra 300. And interestingly, we can do the same type of workflows for other probes, for example, automated nanoindentation, where we identify objects of interest on the surface and take the indents only in the regions that we think that are interesting. And we can determine what is interesting based on the SEM signal, EDS, or any type of structural or chemical metric. And of course, I'm not going to talk about it in detail, but with the automated microscopy, you can do more than just study material. You can also make material. So this is the example of essentially atomic scale 3D printing, when we have the amorphous silicon deposited on the crystalline silicon, and then we use the electron beam in order to crystallize it. So you see how the operator starts to crystallize the silicon from amorphous to the crystalline phase, and essentially creating the structure one atomic plane at a time. Now, for all these applications, the interesting thing is how to make it work effective and how to make it work together. So the obvious way to do that is to say, hey, we have the automated tools. We also need some form of the machine learning agent or agents that are going to interact with the tools and basically orchestrate the experiments. So as all of you know, currently we are in the time when the amount of hype around AI is extreme. So there are a full spectrum of opinions ranging from AI is going to kill us all the way to the opinions that there is going to be the artificial general intelligence in the next 3 years, and the world would be totally different. So you may ask a question, how can we cut through the hype? And the answer is very simple. So the easier way to disambiguate what is real and what is not is to look at only 2 aspects. One aspect is how we make decisions. So what is the role of the human and what is the role of the AI? And the second is how do we execute decisions? So what's the role of the human and what is the role of the automated experimentation? So once you look at these 2 principles, everything else follows. So for example, if we want to make machine learning controlled self-driving labs real, we need to ask ourselves the question, what decisions can be executed? How fast can the decisions be made? How fast they can be executed? How are they improved? So what is the learning aspect in the system? And what's very important is that for each hypothesis that drives our decision-making, we also need to define the experimental action space. So some hypotheses require quite a lot of experimental facilities to falsify. Some hypotheses can be falsified within the single experimental tool. And I will return to this question of the experimental footprint throughout the presentation. Now, before we go there, let's look at what is the state of the art. So I mentioned that the whole ML and materials revolution started in theory about 20 years ago when the Gersider paper appeared, and also at the time when the AWS and cloud services appeared at the same year. So this matters because cloud services allowed us to run the simulation from anywhere in the world as long as we have the internet connection. So before that, you have to build a cluster, and obviously that's kind of expensive and time-consuming. The problem with the theory workflows is that we start with some search space, we go through the set of the filters, then we create some form of the plausible candidates, and then the theories generally say that we need experimental validation. That's a great foundation for science, but that's not how science works, because ultimately what matters in science is the synthesis and then closing the feedback loop, so improving the theory based on the experimental finding. And if we start from MD or DFT type of models, we really cannot improve them much based on one experiment. So this whole question of the experimental feedback in the screening pipeline is something that is essentially wide open. So what happens in experiment? So in experiment, experimental automated experimentation is a much newer tendency. So it started to take off big time only around 2020. And the workhorse here is what is called the Bayesian optimization. So imagine that you want to explore some parameter space, for example, phase diagram or some synthesis space or what's not. So you take a measurement in several locations. So the measurement can be anything. It can be X-ray imaging, PL measurements, and so on. And then you have to do one very, very important step. So the physical measurement are usually giving a high dimensional data set. We need to somehow convert this data set into the single parameter that we care about. So for example, if we take a photoluminescent measurement, we pick the height of the peak, so the quantum efficiency, width of the peak, or the position of the peak, given the bandgap. Obviously, as you can imagine, for X-ray, this can be much more complicated because sometimes if in the X-ray spectrum, we care about the properties of the primary phase. Sometimes we care about the disorder. So for example, the width of the peak, and sometimes we care about the presence of the secondary phases that are known to be detrimental to our application. So this issue of figuring out what is that in the measurement that we care about is actually super important and almost unexplored. So anyway, but then if we find out the scalar that determines how useful the things are, we build the surrogate model. Essentially, we interpolate over the parameter space and we calculate somehow the uncertainty. And then the prediction and uncertainty allows us to construct what's called acquisition function, which balances the risk and the exploration target. How we choose them depends on essentially our experimental limitations. If we have to limit experiment fast, we choose very greedy policies. If we have a lot of time, we become more exploratory. But the interesting thing is that this Bayesian optimization is only a very small part of how the real science works. So for example, if I look at the lab working on the hybrid perovskite synthesis, the chain of the decisions here is much more complicated. You start with some reagents, you can use them to make microcrystal libraries and study optical properties or time-dependent PL measurements. You can make films, study cathodoluminescence, XPS, and make devices, or even make crystals. So some of these decisions, for example, navigating of the composition space using microcrystal libraries, are well available to Bayesian optimization. Others, for example, using the microcrystal library to choose the candidate for thin films. I mean, there are Bayesian methods for that as well. So things like a multi-fidelity or multitask Gaussian processes, if you will. But sometimes we have to make decisions which are much more complicated. For example, sometimes we have to look at the cathodoluminescent data set, analyze what is the phase formation mechanism inside the film, and based on this analysis, we need to change the synthesis protocols. So in this case, or maybe even choose the different end member. And in fact, this is absolutely normal for science in general. So we never deal with a single optimization loop. So the real science always works like a multiple connected loops. So on the one end, we deal with the essentially a lab type of environment when the feedbacks are fast and the theory, if you will, is fairly fundamental. And then we start to move from materials to device prototypes to products, and things become much, much slower. So we can say in general that the fundamental knowledge propagates from lab to the fab, and the value in some sense propagate reversely from fab to lab. The problem is that some of these feedbacks are very slow. So as you know, optimizing battery can take, technology can take years. And also scientific data is always very high dimensional. So how do we understand what value it contains, both in terms of fundamental discovery and in terms of economy, is non-trivial. And then when we were thinking about this type of stuff, the natural question you may ask is whether machine learning and physics are enough to deal with this type of models. So look at this triangle. So let's assume that this corner corresponds to the data-rich methods such as DCNNs, LLMs, and so on. And this corner corresponds to physics, for example, analytical theory, computational experiments, and so on and so forth. You may ask, what's in this corner? And I will pose that this corner deals with the rewards or human motivation. So why are we doing things? So for example, our experiment can be driven by making a better structural material or better energy storage or fundamental discovery. So this is what drives our experiment. And as you can imagine, the reward functions that we use in physics or machine learning are very, very different. For example, the typical reward function in the data is the loss function. And for those of you that are familiar with machine learning, you are familiar with the difference between metrics and the loss function. So loss function is what we can use, and metrics is something that ideally best matching our specific business case. We cannot use it as the feedback. We cannot backpropagate metrics, but we can use it to ascertain the performance of the model. So for physics, the reward functions are things like predictive power or parsimony or whatever, but obviously nothing like this. And of course, there is a whole set of the intermediate reward functions, which are much simpler than these global challenges, but at the same time, much more complex than the loss functions or predictive power. Now, the question you may ask is, what does this guy know about the machine learning in general? And so as an example of very strong confirmational bias, I'll show you a quote from the book by Peter Norvig. So by the way, if you're interested in learning the big picture of what machine learning and AI can do, I strongly recommend reading it. It's kind of probably the best book written about the sort of, if you will, philosophy of the machine learning. And Peter Norvig basically says that remarkably, almost all AI research until very recently assumed that reward functions are known. But the point I'm trying to make is that if you try to apply machine learning in domain areas, most of the time, these reward functions are not known. And in fact, if they were known, then pretty much all problem will become optimization problem, and we know how to solve optimization problems reasonably well. So at that point, so that was about maybe a year and a half ago, I asked the question, so what if rewards are all we need? So what if rather than trying to improve the machine learning methods or get more data, we pay more attention to how we formulate our reward functions? And there is this famous book by Thomas Kuhn. I mean, it's fairly old and sort of there are both positive and negative opinions about it. But one of the ideas that Kuhn pushes is that if you propose a new approach, it should satisfy two conditions. So it should explain previous data and incorporate past theories as special cases, and it should allow to do new things. So for the former, I will argue that pretty much each paper you can read will have the objective and reward function. It's simply what is written in the introduction of why people are doing the work. So for the second one, in order to build the reward function, that has to be a part of your domain experience. So as it happens, my core expertise is the machine learning for microscopy, both electron and scanning probe. So I started to work in this area before 2010. So we had papers using neural networks and supervised learning before 2010. And around 2010, we started to think about integrating ML and microscopy in real time. And that has been something that I have been working on for quite a while. So based on that, there are several levels of the machine learning that we can introduce in microscopy. So imagine that this is your workflow as the microscopist. You plan the experiment, you make a sample. This is your day in the microscope. This is when you go back home and analyze the data. So how can machine learning fit into this scheme? So the first level is the post-acquisition data analysis. Obviously, once you analyze the data, you cannot go back to the instrument and do the experiment differently. So almost impossible. The second level of machine learning is the real-time analytics. So imagine that your instrument streams data. It can be either high-dimensional, or it can be simply too fast, or it can be sampled at very high pixel density. So machine learning can help us represent the data in the form that is more understandable to human. But at this level, the decisions are still made and orchestrated by human. So human looks at the data represented in different form, but it's still the human who decides what to do next. And the autonomy starts at the level 3 when machine learning agent introduces decision. So this is actually automated microscopy. So levels 4 and 5 are how we connect microscopy data to the general physics, so how we incorporate it in the theory analysis pipeline. And the level 5 is an upstream planning. So the instrument basically tells the synthesis robot what next sample to make. But let's talk about the level 3 today, because this is something that we feel we understand reasonably well. So, and it turns out that if we want to understand how to build the machine learning agent that can run the microscopes, first and foremost, we need to understand the human motivation, or if you will, human reward functions that drive the decision making. So imagine that you're looking at the SPM image and you want to choose the locations where you want to take a detailed spectroscopic measurement. So it would be the same thing for SPM spectroscopy. It would be the same for STEM EELs. It would be the same for optical or SEM nanoindentation. So any type of technique that combines the imaging and the spectroscopic aspect would follow the same pattern. So generally, if human makes decisions, so one approach to work with this type of problems is to take the measurements everywhere. So this is something that we have been doing in Oak Ridge from 2004, when I started the program, till 2016. The problem with this approach is that, first of all, your data volumes start to diverge. So we were generating multiple gigabytes of data at that time. And secondly, the experimental times diverge. So running the instrument for dense mapping for several days basically destroys the probe and the sample. So it was becoming clear that rather than taking more data, we need to actually make better decisions. And as I said, human decisions are informed by several considerations, right? In the beginning, you will try to optimize the microscope and do it on the regions which presumably can be used as standards. After that, we can explore the locations which are statistically significant. For example, you see the stripy domains everywhere. If we take measurements at the several locations with the stripy domains, we are probably not going, and the results are the same, we are probably not going to explore other locations because we already know how these regions behave. So after that, we can look at this region because there are clearly some anomalies here. And after that, we can say that, look, this is the ferroelectric wall. This is the region with the high curvature. So maybe we should take measurements here because we expect that there would be signatures of the flex electric coupling. And then some of my other colleagues can say, you know what, these regions are also interesting because there is a high strain here. So notice that the human operator running the microscope does essentially the same operation. So he chooses the locations to take the measurement and take the measurement. But the logic of making decisions is very different. You start with microscope optimization, then you explore the statistically significant regions, then you explore outliers, and then you run an experiment that can falsify specific physical theory. So corollary to that, that if we want to build a machine learning agent that runs the instrument, we need to be able to translate this human basis for decision-making into the language that machine learning understands. And if we know what to do before the experiment, we formulate the policy. So that's essentially a lookup table. If this is what is on the screen, then this is what you should do. But most of the time, we formulate the reward. So what is that we want to discover? For example, improve the imaging or discover structure property relationship. Reward can be sparse, available at each step of the experiment, or myopic, or reward can be sparse, meaning available only in the end of the experiment. However, if we don't have the policy or reward or sparse reward, if we only have a long-term objective, we simply cannot use machine learning to do anything. It's like having the mathematical equation which have equality sign, but nothing on the other side. So in this case, in order to formulate the experiment, we need to have policies or rewards. So the question is, what can be policies and rewards in the automated experiment? It turns out that some of them are obvious, for example, image optimization. Some of them can be something like physical law discovery, if this physical law can be discovered on the instrument. Some of them can be formulated based on the reward functions for image or structure property relationship. So let me show you a few examples. So this is the example of the spectra talking to the supercomputer. So we take images, we send them to the cloud resource. So then we do the image segmentation. So several years ago, we would write our own UNet. Now we can simply fine-tune the SAM from Meta. So we find all the particles, and then we specify the experiment that we want to take yields, EDX, and diffraction only at the centers of each particle. So this is the example of the fixed policy experiment. We know in advance that we are interested only in the particles, and essentially we don't want to waste experimental time in studying things on the grid measurement. We don't want to do the point and click. Our machine learning agent is going to take measurements for us because we specify what is that we want to accomplish. So this is a simple example of the fixed policy experiment. A complex example of the more complex example of the experiment with the defined reward function is what we call the hypothesis learning. So many of you heard about ideas about having machine learning agent that does experiment and generates new knowledge. So most of the time, these ideas are coming from the machine learning community, where the concept of the experimental footprint, meaning the necessary amount of equipment required to falsify a hypothesis, is simply not considered. So this being said, if we have a machine learning agent connected to the microscope, the range of hypotheses that we can explore only on one instrument is fairly limited. But as it happens, for many years, I worked on the problem of ferroelectric switching in scanning probe microscope, when we apply the tip to the surface and apply bias and they generate domains. So this is a type of experiment that can be run only using the microscope. So in this case, we can formulate the hypothesis space. For example, the size of the domain can be determined by thermodynamics, or it can be determined by pinning, or it can be determined by charge injection. So it's one or the other. And then what we can do is we can build the machine learning agent that is informed by this hypothesis and tries to run the experiment in such a way as to determine which of the hypotheses is correct. So the reward function in this case is the predictive uncertainty. We intuitively expect that if the hypothesis is right, then it describes the experiment better. So in order to make a policy for the automated experimentation, we allow the hypothesis that gives the better predictive power to run the experiment more often. And what you see on the screen here is the example of the work done while I was still at Oxford about 4 years ago, where our probe creates a domain. So you see how it scans. We can determine the domain size. That's a fairly trivial process. And then after the domain size is measured, our machine learning agent chooses the parameters for the next experiment. So it tries to figure out what is the next magnitude and length of the bias pulse. And while the machine learning agent is thinking, our microscope deletes the domain and prepares the experiment for the next round. So this is how it looks on the backside. So this is our parameter space. So this is kind of small dimensional hypothesis model. This is how the reward works. So you can see that model number 3 ends up being the winning model. And we know that in this particular case, model number 3 actually makes sense. So it's we don't know it for sure, but in this particular material, the pinning is actually a very likely mechanism. So what happened here is that our machine learning agent basically was given 4 hypotheses, and it ran an experiment to establish what hypothesis is correct. So currently, we obviously can run the same type of experimentation in the University of Tennessee. So these are the few examples of more complex workflows where our reward function is tuning of the instrument. That actually ended up being a very complicated problem because we had to formulate the reward function combining human heuristics and the knowledge of the physics of scanning probe microscopy. We can discover structure property relationship. For example, we can run the experiment to learn where in the sample the hysteresis loops are maximized. Or we can run a simple fixed policy experiment. So this is the experiment when we image the surface and run the supervised measurements of the switching at the locations that we know in advance. So all of this can be run. Now, the interesting thing here is that very often we are interested in optimizing or discovering more than one parameter. So in the experiment that I've shown you before, we were trying to write the ferroelectric domains and see how the size of the ferroelectric domain depends on the bias pulse. But we did it in the material which was almost ideal in terms of properties. So there was no microstructure. It was kind of perfect. Now imagine that we have the material with the complex microstructure. So the properties, capability of material to switch will depend between the different locations. So we still can run the experiment when we apply bias pulse and form the domain like this. But in some cases, the domain would have nice spherical shape. And in some other cases, it would be elongated. So one is determining the ease of switching, another is determining the presence of the pinning centers. So can we run the experiment where we find what is the optimal possible combination between these parameters, what is called the Pareto front? So this requires a little bit of development. So we had to build our own deep kernel learning library for multi-objective optimization. But this is how it works. So now we are running the experiment when our microscope tries to find out in which locations of the sample there is an optimal combination between the pinning strengths and the capability of material to switch. So notice that I showed this example for autonomous microscopy, but exactly the same type of logic can go in any other type of experiment, non-indentation, or even the experiments when you have the macroscopic testing, or even things like molecular discovery, because the basic decision-making workflow is absolutely the same for all these cases. Now, this being said, yes, we can use multi-objective DKL for molecular discovery, but since I'm an experimentalist, for me, the next question is, how can we expand the experimental footprint? So if you have one sample and one microscope, the range of things that you can do is actually fairly small. So one way to expand the experimental footprint is to run the combinatorial libraries. So as you know, combinatorial library is the sample that combines, that has some form of concentration gradient. So it can represent the binary library or ternary library. So you can make a more complex positionally encoded library. So then, and this is the example how it works. So this is the automated microscope, which automatically explores the combinatorial library of the high entropy alloy based on the topography. And there is a machine learning algorithm that tells it where to take the next measurement. And this panel shows the front end. So this is the example of the topographic imaging. This is the library itself. So as you can imagine, these points correspond to this wafer under the microscope. And you can see how the automated experiment tries to discover the Pareto front between the, for example, grain size and the surface roughness. So obviously, I mean, with the roughness experiments, we learned something about the material growth, but it's far more interesting to run these experiments when we explore the functional properties of material. And here, the interesting thing is that scanning probe microscopy is actually an ideal tool to, so we cannot probe the mechanical properties with SPM very well, at least not for hard materials. But we can do it very well for properties such as ferroelectricity, photovoltaics, meaning that we can use it for ferroelectric material discovery or photovoltaic material discovery. And this is the library of the Buchmann ferrite. So the concentration gradient brings us from ferroelectric phase all the way to the orthorhombic phase through the morphotropic phase boundary. So it turned out that if we want to run this experiment, it turns out to be much more complex than just moving around on the sample surface. So the topographic imaging in AFM is relatively robust. Functional property measurement requires tuning the instrument several times, and it requires some form of checks and balances to avoid landing the probe on the dust particles, and so on and so forth. So we ended up building the workflow when we look on the optical image in order to avoid the dust particles. We engage the surface, we have to tune the cantilever scanning probe imaging, and we have to tune the spectroscopy. So it ended up being the multiple step workflow, but in the end it worked. So what you see here is the experimental trace. So the vertical axis is the hysteresis loop area, that's a measure of ferroelectricity. And each point now is an experimental measurement. So it's a Gaussian process, but it's a Gaussian process when our machine learning algorithm interact directly with the measurement system. And you can see that after a while, it actually have found the region where the properties are maximal. So this corresponds to our morphotropic phase boundary over here. So this is the experimental materials discovery. Now, we don't have much time, so I'm going to only very briefly mention it. So notice that one of the very important things in the building the automated experiment is the amount of data that we extract out of the measurement. So for example, for the ferroelectric measurements, for the topography measurements, we have to find our reward function as the roughness or the correlation length. For ferroelectric measurements, it can be a loop area. For X-ray measurements, and so on and so forth. So the problem is that our parameter spaces in which we configure experiment can be much more complex. And the way that we convert the observables into the reward functions can be also much more complex than just choosing one parameter. So imagine I want to explore the same combinatorial library, but use the electron microscopy measurements of the domain structure rather than something else. So how do I learn physics from these images? So the interesting problem that I believe would be a great area to explore in the interface between the physics and machine learning is the creation of the deep image analytics. So a good comparison here would be the things like classical natural language processing when we study with text, which is just a sequence of images on the screen. We find letters, we segment sentences, we tokenize it, we do the part of speech tagging, recognize entities, and so on and so forth. So we start with the text, and then we take each element of the text and add deep meaning to that. So that's how the NLP workflows work. So in principle, for image analysis, we want to do the same thing. So we want to start with imaging and spectral data, clean it, and then do the shallow analytics, and then try to convert it into the physics of the system. So much like our colleagues in astronomy can learn laws of mechanics from observation of planetary motion, we want to learn the fundamental physics from the observation of the atomically or mesoscopically resolved imaging. So it's very difficult to make it work by the ML simply because this gives rise to very non-myopic workflows of how we can analyze image data. And it turns out that reward functions also allow us to solve this type of problems. So in other words, the analysis workflow for images that can comprise multiple steps can be represented like an optimization problem in the joint parameter space of each operation or in the combinatorial space of image of possible operations. Interestingly, it works. So we can use the unsupervised learning in order to segment the images in the unsupervised manner. And if we have multiple rewards, then we also have to deal with the Pareto front that allows us to do that. So the nice thing about this type of workflows is that they're unsupervised, which means that we can deploy them on the active instrument. And this is the example of this unsupervised reward workflow running on Spectra. Now, the last thing that I want to briefly mention is the fact that if we have the reward functions, we can actually dynamically change them during the experiment. And this opens the way for the human AI interaction in the most natural manner. So let me illustrate how this idea came to be. So for example, if we run the automated experiment, when we try to discover which microstructural element has highest nonlinearity, you can see that here we had some healthy exploration. And then our algorithm went to this location and got stuck here. And for this sample, the algorithm clearly is getting stuck in these two locations. So what's going on? What's going on is that we define the reward function before the experiment, but then we expect the experiment to be successful with the static reward function. And it's roughly the same thing as choose the direction on the road, press the acceleration on the car, and not try to rotate the wheel. So you can get pretty far, but sooner or later you will get off the road. So it turns out that once we build the myopic optimization workflows, they allow a very straightforward way for human AI interactions, because we can change the definition of the reward function during the experiment. And we can dynamically tune the exploration-exploitation balance during the experiment. So the question is, how comes we can do it in the experimental physical sciences and not necessarily in the machine learning community? And the answer is that we are starting from the totally different footprint. So until now, all the experiments have been done by humans. So we are familiar with how to run our experiments and how to monitor their progression. So guess what? If we delegate the decision-making to the AI agent, we still can monitor the experiment. So we can, for example, look at the sequence of the points where the AI agent made measurements. We can analyze what type of features AI agent have chosen to explore. We can even monitor the progress of how fast the AI agent learns the structure-property relationship. So, for example, does the kind of how the predictive uncertainty evolves with time. And this can be implemented in real time. So obviously I cannot show you the human-in-the-loop workflows running on actual instrument, but this is the recording of the ML agent running the spectra. So it runs the instrument for several cycles, and then the human observes the progression of the experiment, and human can decide to intervene on the reward function or intervene on the exploration-exploitation balance. So where are we? So the current generation of the physical tools is roughly here. So we have humans who sit in front of the microscope. Human look at the data streaming from the screen, so imaging the spectra, and human issues the basic commands to the instrument. So the tools that I've shown you is basically the next step. So when there is a machine learning agent that issues the commands to the instrument, and the machine learning agent have access to the imaging and spectral data. So human can intervene directly, but generally we expect the human to observe the behavior of the ML agent and intervene on the rewards or policies. So what's the gain here? The gain here is that most of the microscopes are sort of faster than humans. So electron microscope can be operated at that level of the tens of microseconds, sorry, milliseconds, and potentially faster. So at the time when the human can make one decision, machine learning agent can have 100 decisions. So maybe these decisions are not as good as human, but the value proposition here is rather obvious. And another very interesting thing is that once we start to run the ML agents in terms of the reward function, we basically build the bridge to the whole community that works on the large language models, reasoning systems, and so on and so forth, because it is possible to convince essentially ChatGPT to formulate the plausible reward function and actually run the Python code that implements it. So in some sense, we build one of the possible bridges between the actual physical tools and the LLM-based reasoning models. So to finish my presentation, so we hear a lot about the big data and machine learning. And all of us know that the current driving force behind the industrial development of machine learning is the belief that large models and the large volumes of data are going to change the world. From scientific perspective, this is not completely correct. So big data is useful in the well-established fields with the plenty of real applications. So if we have a lot of data in fields like medicine and biology and so on, or semiconductor industry, big data is the way to go. But in science, we always want to go to where no one has gone before. So that means that by definition, we don't have a big data there just because the area is new. But reward functions, they can convey the logic of the human decision-making but not the prior human knowledge. So of course, it is not going to substitute the big data, but it's going to complement it for more exploratory tasks such as we are doing every day. And LLMs can help us do that. So that's something to be discovered. So two things. So first of all, I think that's a space of opportunity. If you look at the dynamic of the workforce, a lot of people 10 years ago went into ML from fields like MDFT, MD, or finite elements. So by now, many of them are coming back and building the activity in this area. But the domain applications of ML is a very different field. So people who do DFT-MD very rarely switch into the experimental sciences. I know some of my colleagues have done it, but generally it is very unusual. So for those of you that are experimentalists, so at this point, sky is the limit because we clearly see that the new field is opening, and it requires a qualified workforce to start it. And it's also kind of interesting to speculate how the future of multiple ML agents and multiple connected instruments is going to look like. So obviously, if you think about the parameters about this future, you have idea of multiple humans interacting with the multiple AI agents, interacting with the multiple resources, essentially tools. They have to learn. They have to deal with some economy because resources are finite. So if you put all this consideration together, it's very possible that the future of the automated experiment will look in some sense as the giant online role-playing game. So it can be not only scientific interesting, but also fun. So I would like to stop here and take any questions.